Hello, I'm Dan Reagan. I just wanted to do a little video for you today. I'm diverting myself again back to the SpaceX group and the NASA group. I heard people talking about going to the moon and how long it takes to get to the moon, and this poor person was so frustrated. They said, I don't know how long it takes to get to the moon. Well, back in Apollo, it took us anywhere from 66 hours to 84 hours to go to the moon. And that was due to various factors, sweep angles of the different types of trajectories that we used, and so forth. And then now, I think if we could get to somebody like Chang Diaz and his method, Dr. Chang Diaz, one of the shuttle astronauts, came up with a system called ion propulsion. Now, ion propulsion is something that if developed, we could probably get to the moon in 4 hours or something like that. So, yeah, I mean, really, you could decide the amount of time it takes to get to the moon. There's no such thing as one time to get to the moon. We took 3 to 4 days. We can do that again. But, if it's the difference between driving, walking and driving your car. And if speed is the idea and getting things done quicker is the idea, then the Chang Diaz method's going to work. Imagine taking off, and then here you go, and you spin your engine around. Ooh, you spin your engine around, and what happens? You slow down when you spin your engine around. Now, when you spin it back again, what happens? You speed up. This way, slow down. Okay, and that's the whole concept. You stop the engine when you're going super fast, and then spin it around and slow down again. That's the whole concept behind the process, and that shaves a lot of speed, tons of speed off the trip. And so here's my idea of what their command module might look like. And you see, you could stand right over there. You could stand. It's got a couch, a control, computer and stuff, a storage experiment. And I figured this thing might have to be somewhere around 18 by 20 feet, 18 up, heat shield, and 15 feet across. Okay, let me show you that a little bit closer. My idea of what it ought to be. And you see, with a G-force pushing in on you this way, from the other side, it's pushing on you, and then you could stand up in this thing. So that's kind of a cool possibility. All right, let me show you what I think a good timeline might be for a starting mission. Let's say we wanted to go around the moon 3 times. You could spend most of your time at the moon. If you look at this chart here a little bit closer, what you're going to find is that you spend hardly any time taking off, most of your time at the moon, at the points in between, and then very little of your time going home. So how did I figure all this out? How do I actually know all this? Well, the first thing I got to show you is all the variables that I used for it. First of all, I was using an XY graph. Always draw a picture if you're not too sure. And always define your variables. And there they are. See, that's feet per second. And then we go to time, we go to distance and the function and the rate of change and then the derivative. And okay, that's for TLI, that's translunar injection, transcoast, and then we go to LOI, that's lunar orbit insertion. So I'm only going to take you on the first part of the journey. I took you through the whole thing, on the graph. Now, this graph here uses those equations. In other words, we're saying that delta F equals delta X over delta Y. In other words, the function of Y is equivalent to is a function of the delta X over delta Y. And so that defines the function. And then there you see we've got the number of hours. And look at all that time at the top. That's the mission time that we spend, at speed. And that's how long it takes to actually get to the speed, although the whole time we're going 16 feet per second. So it's continual acceleration until you get into lunar orbit on the other end. Here's where you lift off. The lunar orbit comes in over here. Once you get into lunar orbit, it's a whole different story. And there's only 3 equations used. Delta F equals delta X over delta Y, or the speed equals the acceleration times the time squared, equals the secondary speed, which is the orbital speed right before you shove off and go there. That's really all the equations you need. And then, of course, y is a function of x. Y equals fx. Okay, we're good with that. Now, the explanation of the 3 equations, here we go again, it's the same thing. Delta f equals, delta x over delta y, which is really, when you break it down, it's the same things that are on the graph. Same thing down below, s equals at squared plus s, and y is a function of x. Okay, so now And that means nothing changes. That's at the top of the graph no matter how you do it. And then I'm going to try to let you read this a little bit here. Yeah. Get a little closer. Here, let's go from left to right. I think that's enough. Okay. I think that's the explanation of what it is I was trying to do. And yes, sometimes you have things that change, and other times you have things that don't. You have dependent and independent variables and things like that. And most of the graphs you draw are going to be all curved all over the place. But this one is not. In Apollo, believe me, they're all curved, and there's a lot more delta involved, and there's a lot more constrictions. On something like this, it's not as constricted, and you get to draw a lot more straight lines, and that's pretty unusual for a spacecraft. Okay, so take care. Hope you enjoy Dr. Chang Diaz's invention. It's a great invention. Now all they have to do is develop it, get it to where it's got better shielding against the plutonium that's going to go with it eventually. I hope I stay alive long enough to see it go into action the way I'm thinking of it here, because it'll be grand. And then eventually you could go with, start taking a lot of people, build bigger spacecraft, take a lot of people with, and just have a lot of fun in lunar orbit. Or, connect up to a lander, make that lander go down and do some more lunar exploration. Personally, I think 6 times is not enough, and people make a big deal about 6 times, but I think 6 times is it's really nothing. It's nothing to make it gets me that excited. I thought we should have gone about 10 times, but some people get all excited. Oh, geez, we went to the moon 6 times. That can't be true. I can't even remember it, or something like that. Well, just because you can't remember it didn't mean it didn't cost 10 billion work hours to get there, and $1 billion, and 1 million people's sweat on their brow, and their deaths as well. Yeah, that all did happen, and it's too bad they quit so fast. 6 times, now come on. I could see them making a big deal if we were still going today and saying, now come on, this has all got to be a fake. But for 6 times, who cares? We need to go back. All right, take care. Bye-bye.